Hi, I'm Gayle Laakmann McDowell, author of Cracking the Coding Interview. Today we're going to cover the continuous median problem. The continuous median problem goes as follows. You have an array of numbers that you're reading in, one after another, and after each number you want to print the median of all the numbers thus far. So how can we do this? Well, first, let's remember what a median is. A median is the value in a list of numbers for which half the numbers are below, half the numbers are above. That is, if you were to put them in sorted order, then it'd be the midpoint. If there's two midpoints, as in there's an even number of values in the list, then the median is the average of those two values. So how can you do this? Well, one way is, of course, to just keep a sorted array, and then as each number comes in, put the number in sorted order, shifting values over as necessary. That'll work, but it's pretty slow. It'll take n squared time. So what's a faster way of doing this? Let's remember that a median is the number which half the numbers are below, half the numbers are above. So rather than keeping everything sorted, which is kind of unnecessary, let's actually just keep two buckets of numbers, one which is the lower half of numbers and one which is the upper half of numbers. Then when a number comes in, look at its value and determine whether it's in the lower half or the upper half. We want to keep these two buckets pretty balanced too, so they shouldn't be ever different in size by more than one, so we want to be roughly half on each side. Then to get the median, we just need to pull out the appropriate value. If the buckets are different sizes, then take the bigger bucket and pick either the min or max depending on whether it's the lower half or the upper half. If the buckets are the same size, then take the biggest element from the lower half and the smallest element from the upper half and average those. Well, that's all well and good, but how do we actually do this efficiently? A heap is the perfect data structure for this problem because this allows us to very efficiently pull out the biggest element from a bucket or the smallest element from a bucket. So what we can do is we can keep a max heap of the lower part of the numbers and a min heap of the upper part of the numbers. And then we can very efficiently add numbers as well as pull out the min or the max. So let's turn to the code now. So this is our function called getMedians, and it's going to take an integer array and return an array of doubles. Remember that we need to use a double here to store the median because the median might be an average of two different integers. So I'm going to cheat a little bit to just get started and give ourselves two heaps. So these are actually in Java priority queues, but they're implemented with heaps. You could also use a custom built heap, but most languages have some sort of functionality here. So here are two heaps. We have lowers, that is the heap for the lower portion of numbers, and this is actually a max heap. And as you can see, what I've done here is I've given a custom comparator that says, hey, rather than storing it with the minimum value at the top, let's put the biggest value at the top. And then this is hires, which is a min heap for the higher half of numbers. So a min heap on the higher half and a max heap on the lower half. The very first thing I'm going to do is just outline what the code will look like. I'm going to have an array of medians, and I actually know my size, thankfully. So it's going to be of the exact size array.length. And then I'm going to iterate through all values in the array. So I++. Okay. And now what I'm going to want to do is a couple different steps. The very first thing I want to do is just essentially get the skeleton of my code done. So I want to get the number out of the array, and then I want to add it to the heap. So add number. I'm going to call another function to do this. That's going to take care of my kind of real work here. So add the number, and then I want to, my second step is to rebalance it, the heaps, so that each heap has roughly half the numbers. And then, oops, a little typo there. And then I want to go and get the median back. And so medians of I equals add number, or get median of lowers and hires. And then go and return that value. So that's the basic of the code. And this strategy is exactly what you should do in the interview. Don't write all of this code in line, the add number, the rebalance, the get median method. Just call out other functions that do it. And the nice thing is that this demonstrates great coding style because modularization is really important. It also makes it much easier to conceptualize the code, that it's like, okay, step 1, step 2, step 3. And then also, if I get cut off right now, at least I have the basics of my algorithm done. From here on out, it's just filling in the details. The next method I want to write is this add number method. So this is going to not return anything. It's going to take in, call add number, and I'm going to call this, I'm going to take in my number, my priority queue for the lowers, and priority queue for the hires. And now it's pretty simple. If lowers is empty, or the number basically belongs with the lowers. So if number is less than lowers.peak, then throw it into the lowers. Otherwise, throw it into the hires. Pretty straightforward. Okay, now I just have two more methods left to do. And I'm going to go ahead and just copy and paste these method signatures in there. So what rebalance will do is it'll compare the sizes of the two heaps. And we want them to be as close to the same size as possible. So if they're the same size, fantastic. If they're off by just one element, well, that's the best we can do. But if they're off by any more than that, then we want to shift elements from the bigger heap into the bigger size heap, not the bigger values, bigger size heap, into the smaller one. So I'm going to cheat a little bit and just copy and paste some code in here. So this is simple code that basically lets bigger heap equal the value of whichever heap is larger, and smaller heap equals whatever heap has fewer elements. So now what we need to do is just compare the sizes of the two heaps. We want them to be as close as possible to the same size. So if they are actually the same size, then great. But if they're off by more than 2, or by at least 2, then we really need to rebalance them. So if bigger heap dot size minus smaller heap dot size is bigger than 2, and actually it should never be, is at least 2, it should never be bigger than 2, then take one of the elements from the bigger heap, and specifically either the minimum or the biggest element. So take the top element from the bigger heap and add it to the smaller heap. So smaller heap dot add of bigger heap dot pull. So pulls, you remember, is actually going to pull off the top element, remove it, and return that element. So it's going to add it into the smaller heap. Now our final method is getMedian. So what getMedian will do is it'll first look at the two heap sizes. If they're different sizes, then take the top element from the larger heap. If they're the same size, then we need to average them. So we're going to first figure out, which one's the smaller heap and which one's the bigger heap. So just reuse the code from above. Now, if bigger heap dot size is smaller heap dot size, then this is where we'll want to average the medians. Otherwise, return bigger heap dot peak. So this is when, that's the case when the heaps have different sizes, so there's an odd number of elements, and so the top element in the bigger heap will actually be the midpoint, or the median. Otherwise, if they're the same size, then go and get the top element from each and average them. So you might have noticed, at least if you're a Java coder, a very subtle bug here. Remember that when we do integer division in Java and in many other languages, if it's not an integer, if the result is on integer, the value gets truncated. So we're going to want to cast this into a double. Very important, and this is a really, really common bug for candidates and in the real world too. So we want to truncate this, or we're going to want to cast this into a double. So now let's run the code and see what happens. Perfect. So we pass this test case, and that's great to see. Let's submit our code and see if we pass all of the test cases. Perfect. We passed all of the test cases by writing this code very efficiently. So remember, whatever programming language you're working with, look it up to see if there is an implementation of a heap. Java uses priority queues, and your language might as well. Why don't you give this a shot now on a new problem?